Here is the equipment set up for the Malus's law experiment using a horizontally polarized red laser. The laser beam will shine down this tube, strike the photodiode, and generate a current which is proportional to the light's intensity. In other words, the brighter the light, the higher the current. We will be measuring the voltage generated by this current and observing how the voltage, and therefore light source intensity, changes when we put different filters in front of our laser. We are also using two half mirrors, which act as density filters, blocking roughly 75% of the photons coming out of our laser. If the laser was able to shine on the photodiode sensor at full strength, the sensor would get oversaturated. So we have to reduce the number of photons coming through in order to get clear results. The goal of this experiment is to observe the effects of polarizing filters on the intensity of our light source, and we have three combinations of filters. The first is a single polarizing filter, as you see here. Virtually all of the light shines through it. This one we'll call 0 degrees, or horizontally polarized. Next, we'll take another polarizing filter, turn it 90 degrees with respect to the first so that it is vertically polarized, and place it directly behind the first filter. Now hardly any light can pass through these two filters when they are stacked. Finally, we'll take a third filter, turn it about 45 degrees, and place it between the other two filters so that we have three filters stacked together at 0, 45, and 90 degrees. You can see that quite a bit of light can get through the three filters when they are lined up properly. Use your knowledge of Malus's law to explain this effect. There are two valid explanations here, one based in classical physics, the other in quantum principles. But you should be able to explain this effect using only Malus's law and some trigonometry. No quantum mechanics are needed. To start the experiment, we'll turn on the laser and shine it at the photodiode to measure the intensity when nothing is blocking it, which you can see here. Right now, the digital multimeter displays the voltage at a little more than 6 volts. Now, even though we have a shroud covering the photodiode sensor, some small amount of ambient light can still pass through and will be in our measurements as background noise. Let's quantify it by blocking the laser beam with a piece of paper. When we do that, the only photons generating a voltage will be from our background noise, which looks to be around 0.2 volts. Now we're ready to test our polarizing filters. First, we'll use the 0 degree polarizer. Ideally, 100% of our light would pass through. Here, because we are dealing with imperfect polarizers, the voltage will dip slightly, but it still remains close to 6 volts. Second, let's test our 0 degree and 90 degree filter combination. In a perfect scenario, this would block 100% of our light and our reading would drop to 0. Here, some small amount of light is still getting through, but it does decrease significantly. Finally, we'll use our three polarizer combination of 0, 45, and 90 degrees and see how much our light intensity changes. Here's an interesting question to think about. Do you think the order of polarizers used here would impact the result? What if we stacked them the other way so that the light had to pass through the 90 degree polarizer first? What do you think would happen? Hint, remember that the laser is polarized horizontally at 0 degrees. Now we can compare the theoretical results based on Malus's law and the actual experimental data we just collected. How closely do our numbers match up with this theoretical ideal? How do you explain the discrepancy? You should be able to do these calculations yourself using Malus's law, and you should understand how any experimental error may have been introduced.